Hi geometry students, this is the chapter 5 review. So you'll see me going through the 25 problems in the chapter 5 review. You can just kind of hit and miss, or you can find the ones you need to work on and just check those out. You don't have to watch the whole thing unless you feel like it would be helpful for you. Okay, so let's get started with number 1 here. First of all, if SQ is the perpendicular, ray SQ is perpendicular bisector of segment RT, explain how you know that RQ is congruent to TQ and RS is congruent to TS. Well, why would that be true? I've brought up all the lessons from this before, from this chapter. This is 5.1. Why would that lie, or why would that be the case there? And so you could look at the back of the book and see what to do here, but I'm going to use the theorems. They'll state it in a slightly different way. So I could say that AC, BC are congruent by the perpendicular bisectors theorem, and then the converse would say that D is on the perpendicular bisector. So if we look here, we're going to say that these two are congruent to each other, RS and TS, by that perpendicular bisector theorem, just like you see here. Same sort of thing going on there. And RQ and TQ, if that's the perpendicular bisector, if SQ is a perpendicular bisector, that means by definition it cuts it in half, saying that that and that have to be congruent to each other. So it's based on those two facts. So we'll just write it the way the back of the book has it here, though. So if a point is on the perpendicular bisector, of a segment then that point, I should say, I should word it differently, then it is equidistant from the endpoints of the segment. So let's check out number 2 from there. If UR is congruent to UT, what can you conclude about U? Well, if that's the case, when we look back here, that's where this is going on. So D is the same distance away from A as it is from B. That means it has to lie on that perpendicular bisector. So we conclude that it actually lies on the perpendicular bisector, so that we can say U is on the perpendicular, remember that's our shortcut symbol for perpendicular bisector of segment RT. And then number 3, if Q is equidistant from ray SR and ray ST, what can you conclude about Q? Well, that would have to lie on, we could say that this and this are the same angles then. So this is still from 5.1, but going back here, we're saying that this is equidistant from this. That means that it is actually on the perpendicular bisector based on the theorem here. So we can say that Q is on the angle bisector of the big angle here is RST or TSR. So I'll go with RST. So let's move on now to numbers 4 and 5. So these are the perpendicular bisectors. The triangle RST intersect at K. Find KR from this first one. So we know from before, I'm just going to draw this in. This isn't something you would have to do necessarily, but we know that this is the case. Kind of just brainstorming some ideas now that might be helpful. That is really ugly looking. Let me make a better circle out of that. Okay, so that's looking better, and we could also put in an extra segment here. So let's do that now. We could say they've drawn this one in, they've drawn that one in. I could even draw this one in and make that a little thinner. I could have an extra, yeah. Didn't lift my pen again, there we go. So that's all the same here, so I could put 4 marks here, here, and here if I wanted to, just to keep it a little cleaner looking, though I won't do that. So what can we say from here? The perpendicular bisectors of RST intersect at K. This is a circumscribed circle. We have our peanut butter can, that's the perpendicular bisectors and circumcenter. So we're trying to find KR though. So how can I find KR? Well, if this is 12 right here, and this is 32 right here, I can kind of work my way from there. So a little sneaky trick, I think, to see here. I'm going to put 4 marks here, 4 marks here, and 4 marks here. Okay, so all these things are congruent. Let me make that a little cleaner looking. 4, okay. And so I'm going to use this triangle specifically right here to help me figure out this. Because if I can figure out KS, then I'll know what KR is. And so it looks like they give me enough information for that. They tell me that this side here is 12, and they tell me that TS is 32. So I'm going to redraw a triangle down here, in the one that's going to help me actually figure this out. So this is 16, this is 12, this is K, this is S, and then this point doesn't really have a label, so let's just call it, let's go with Q. I don't think we've used that here, no. So 32, where did 16 come from? Well, this was the same as this, so that means I cut it in half. I have 16 here, 12 here. So what is KS? How do I solve for KS? I can use the Pythagorean theorem. So I'm calling this Q. This is a right angle based on it's there in the picture. And so I can say that 12 squared plus 16 squared, those are the two legs squared, would equal KS squared. So I'm going to solve that for KS. Could you replace this with X? Sure, if you wanted to. Be totally fine. This would be that, which is 400. You add that together. And then from there, you can take the square root of both sides, take the square root of 400, take the square root of KS squared, and that will cancel out here and here. Get rid of that. We'll have 20 equals KS. And since KS has to be the same as KR, being a circumscribed circle around there, being these radii are the same, we could say also that KR equals 20. Alright, so looking at number 5, I see a similar sort of idea that would work on this one. Let's take out my compass here, and I'll use orange. I'll make it small. So angle bisectors. Remember our little clever trick to help us remember this, our clever way. We have peanut butters. Peanut butter can always be used in my cookies and Oreos. So this is perpendicular bisectors and circumcenter. This is angle bisectors, and I think I messed that up there. Can always be, I said used, but there's no used. Can always be in my cookies and Oreos. My fault about that. So this should say just I cookies and in my, wow, in my cookies and Oreos. Okay, so this is angle bisectors goes with incenter, medians goes with the centroid, and then the altitudes or heights go with the orthocenter. Altitudes. And so with this one, we're talking about angle bisectors. We can have that incenter. We can have that inscribed circle within this triangle here. So I'm going to place my compass point at W, and move this in so that it just touches the sides there. Rotate this around. There we go. So it just touches the top there. Okay. And then there's my inscribed circle right there. That means this and this distance, and I could also draw in the distance down here, here to here would all be the same. And so I'm trying to find what's WB. They give me enough information here to find WA, and if I know WA, then I also know WB. I know that these three guys, these three segments are all the same. So this is 8, this is 10, that would let me figure out WA. So I'm going to kind of highlight the triangle I'm looking at here, looking at this triangle, and I'll redraw that triangle down here. So we have W, A, and Y. This is a 90-degree angle, this is Y, this is 8, and this is 10. So we're trying to figure out this is our missing side this time. So I would say something like WA squared, that's one of my legs, plus other legs squared, 8 squared equals 10 squared. Solve this for WA. Could you replace that with X or any variable you wanted to? Sure, if that helps you. Go ahead and do that. So this is C there. And subtract 64 from both sides. Left with WA squared equals 36. Take the square root of both sides, and you got your answer. WA is going to be 6. At least you got your answer for WA. And because WA and WB are the same, we can say now so WB is also going to equal 6. Alright, so let's get rid of this. Name the special segments and points of concurrency of the triangle. This one should be pretty quick here. So the special segments, looks like I've cut the angles in half here with each one of those. So that was angle bisectors. And the point of concurrency, if you don't remember, always think back to this right here. So peanut butter can always be in my cookies and Oreos. This all goes together like this. So this is angle bisectors goes with the incenter. That is, the incenter is this point right here, that point of concurrency where they all meet up. Number 7, looks like, what have I drawn here? These are all midpoints. I see that this and this are the same. I see that these two are the same. And I see that these two are the same. So I've got all the midpoints, and it looks like I've done perpendicular to those. So I've bisected the sides, and I've got segments that are perpendicular. So this point would be where the perpendicular bisectors meet. So this is perpendicular bisectors, and that's peanut butter can. That is perpendicular bisectors is the circumcenter. This next one, you just have all the midpoints, and you connect those to the opposite vertices. So this is the medians, and where the medians meet is called the centroid. That's the my cookies part of our little catchphrase to help us remember what's what. And then this altitudes here, because you have the opposite vertex being connected to the opposite side with a perpendicular line. So this is altitudes and Oreos, that goes with orthocenter, the Oreos parts. Okay, for numbers 10 and 11, I'm going to get out my ruler. I would suggest you do the same and make a nice graph. If you don't make a nice graph, this problem will be much harder here. So XYZ has these coordinates. So I'm just going to draw the graph out, and then I'm going to pause that while I do that, so just to save us a little time here in the video. But before I do all that, notice here that X values are only going to be negative or 0. So I'm just going to draw this coordinate, or this quadrant right here, the quadrant 2. 1, 2 is the second quadrant here going in that counterclockwise direction. And the Y values are only 0 or positive. So I'm just going to have going up to like 7 or so, and then I'm going to go back 5 in this direction. So I'm just going to draw that second quadrant. Alright, so I've drawn my graph here, and I'm going to plot my points now. I'll use red to do that. And so I've got one point right here at 0, 0. This is point X at 0, 0. Point Y is going to be at negative 4, 0. And point Z is at 0, 6. So point Z would be right up here. Just connect those with some straight lines here and make a triangle. Alright, and now let's do a rast here. We're supposed to find the coordinates of the indicated points. So I'm going to put my ruler off to the side. There we go. So number 10, I don't want it to be that thick. There we go. So number 10, finding the centroid of triangle X, Y, Z. So the centroid, that's where we connect the median. So we got to find the midpoint, connect it there, and do all that work there. So I think I'll draw this one in green. So we'll go with green for the medians here, and we'll use the light lines. Okay. And so first of all, I want to find the midpoints of each side. So this is going to be midpoint there at 0, 3. Over here is -2, 0 is the midpoint in that case, and this way, halfway between 0 and -4 will still be -2, and then halfway between the 0 and the 6 will be right there at 3. So this is the point 2, 3. So connecting these medians, or drawing in the medians, I should say, will look like this. Have something like that, connecting opposite vertex to opposite sides. So we need to figure out what is that point right there. So we can go back to, I think this was 5, 2. We can use the idea, let's see. That's what I meant to say, 5.3. This is less than 5.3. We can say the larger part is 2 times bigger. So thinking of that will let us figure this out a lot easier. So this larger part, why don't I look at this one specifically? So that one seems like the easiest one to me to look at. So what's this larger part going to be? It's 2 times bigger. So if you have this distance from here to here, this is 0, 3. So this is 0.03 right here. This is the point -2, 0. And up here is the point -2, 3. That was all these midpoints. So if this is 0 down here, this is 3 here, 2/3 of that will give me this point. What's 2/3 of 3? Well, 2/3 of 3, this is for the x coordinate. This is kind of expanding our thinking on this a bit. This one is a tougher one, I would say for sure. But the x coordinate is going to be 2/3 of the difference between the x coordinates. So 3 minus 0, 2/3 of the 3 minus 0 is 2/3 of 3, which is just 2. So the x coordinate is 2 for this point right here, I'm saying. And then what's the y coordinate for that? So now we're going to be taking 2/3 of the difference between here to here. So 2/3 of the difference between 4, -4 in this case, and 0. So what's the y coordinate? We're doing 2/3 of the difference of the y values. So here we have -4 minus 0 would be the difference in the y values. You have 2/3 of -4. That's my x coordinate right there. 2/3 of -4. You can put this over 1. You can say that's -8 over 3. And want to make a quick correction there on my thinking. This would actually give me the larger value from here to here. So I don't want the value from here to here, I should say. So from here to here. I want the value from just from here out to here, because that's going to be the actual coordinate. So I want to go here this way. What is that y coordinate going this way? And this is actually my x coordinate. I'm getting all mixed up on this one. I should change this to y and this one to x. Sorry about that. And so this one I should change. I want to figure out what's just 1/3 of this. Let me try to re-explain that just a second here. So this being the y coordinate, this is going to be correct. You can kind of eyeball it here, and this one's pretty easy to see that it's 2. But remember, it's just the 2/3 of this. So it's kind of like the 2/3 of 0 to 3 gives me that y coordinate right there. It's 2/3 of the way up, and then 2/3 of the way over this way, or 1/3 of the way over this way, gives me this x coordinate here. The other 2/3 will give me from there all the way to the end. So this x coordinate would just be 1/3 of that, because I just want to take from here to there. What's 1/3 of that? I could say it's 2/3 of the difference from 0 to -2 instead here. So there's different ways to think about this one. This will do it for me though, and get me the -4/3. So what is my coordinate for the centroid? The centroid is going to be at -4/3. Could you say -1 1/3 or -1.3 repeating? Sure, you could say that too. The centroid is going to be right there. Then for the orthocenter, I'm going to use orange for that. So orthocenter goes along with, this is in my cookies and Oreos, so altitudes. If I were to draw the altitudes in for each one of these, this is what the altitudes would look like. So altitude for this side, remember it's just connecting the opposite vertex to the opposite side and making sure it's perpendicular. And so this would look just like this. So you'd say this, connected here, there's an altitude right there, because it's perpendicular right there. What's the altitude for this side? For this vertex to this side, it would also be looking like that. And so this one, same right here, so it looks like they're lining up right there. If I were to draw in the line perpendicular from here to this side, if I were to take out my protractor to do that, I think that's a good idea. So let's move this over here, make sure it's lined up perfectly with the vertex and with the opposite side so that it's right at 90 degrees. Slide it up just a little bit, and just like we thought, if the picture was drawn correctly, this is what should happen. Right here we connect that, this is perpendicular here. So where is the orthocenter? This one's a bit easier to figure out. Orthocenter is right here. So right where they all meet. So orthocenter is at 0, 0. Okay, so let's move on to 12 and 13. And it looks like I'm going to have another graph to draw here. So I'm going to draw this graph. It looks like they're all positive values. So I'm just going to draw the first quadrant. I don't need quadrants 2, 3, or 4 in this case. So why don't we go, looks like biggest x value is 8, the biggest y value is 4. So I'm going to go 10 in the x direction and 5 in the y direction. I'll pause it and draw the graph first. And so there we go, there is my graph, and I'm going out. So I'm going to draw in my vertices for each one of these. They rhymed, wow, vertices and these, very nice. And let's see, so I'm just going to draw points here. Why don't I do this in red just to make it stand out a little bit more. So H, J, K, we got the midpoints of the sides of this triangle are what you see here. So the midpoints are going to be drawn in here. I actually may have to extend this graph out a little bit based on that fact. We'll see though. Let's just draw this and we'll extend it if I need to. So L is at 4, 3. Should have read that a little more carefully, seeing that those are the midpoints, not the actual vertices of the triangle. So this is at H, this is 5, 6, 7, 8, and 3. So here's another point right there. And then N is at 6, 1. So here's 6, and here's 1 for those values. So drawing a careful graph, very important here with this question to be able to do this question correctly. So let's draw in the sides there. These are the midpoints, not the actual sides of the triangles themselves. Just the midpoints of the sides. A little better there, that's better. Okay, so hopefully you can see the slopes of all of these, or we can figure those out. I can see the slope of this one is straight across, so it's just a slope of 0. I'm going to label all these points with what they should be. This should be M. Here, this is M at 8, 3. This is N at 6, 1. And this is L at 4, 3. And so I can tell, looking at this, that this is going to be the actual triangle. It looks something like this right here. So if I figure out the slopes of these other sides, of these sides, of the midpoint sides, then I can figure out the slopes of the other sides of the triangles themselves, because the slopes of the sides, the midpoint sides, are supposed to be parallel to the slopes of the sides of the actual triangle. So I don't think I need this anymore. Let me close that. If I do, I'll just bring that back up quick later. But let's do number 12. And we'll do that in green. Okay, so here I'll do the work necessary to calculate the slopes first of all. So the slope of, do this in red since it's matching up with what's here. The slope of LM, let's start with that. That one's really easy because the slope, it goes straight across, so I can just say that one's 0 without doing any work on that one. What's the slope of NM? So if we look at this, what's the difference in the y values? Remember, it's y2 minus y1 over x2 minus x1. Difference in the y values over the difference in the x values. And I always make the rightmost point my x2, y2 point. This is my x1, y1. So I'm going to say that this is 3 minus 1 over 8 minus 6. In other words, that's 2 over 2 or just 1. So the slope of this, you're going up 1, right 1, up 1, right 1. And the slope of LN, this line, that looks to be similar. It looks like you're going down 1, right 1, down 1, right 1, but just plug in the numbers too. So let's call this x1, y1, x2, y2. You have 1 minus 3 over, so this one minus this one, and then same way, has to be done the same way there, 6 minus 4. So this would be negative 2 over 2, which is negative 1. So the slopes here, here, and here, those are all important to be able to figure out the slopes of the other sides, the actual sides of the triangle. And so I'm going to, in green, plot some new points that will represent the sides of the triangle. So this is up 1, right 1. I'm going to go parallel to this side right here. If I go down 1, I'd go to the left 1. So I'd have another point here, I'd have another point here. This would be like negative 1 over negative 1 is the same as positive 1 over positive 1. Positive 1, positive 1, got another point here. This would continue going up in this direction. But let's just draw in the segment at this point. Drawing this in kind of lightly, you might say. I'll move that down just a shade there. There we go. So that it just touches all the points. It's just touching there and just touching there. The one at the bottom is going to be a slope of 0, so I can just draw that just as it is. So it should be at the same level. It should always stay at the level of 1 for the y value here. Okay, so that's just touching every point there. And now this one, if I go down 1, I should go to the right 1. So down the right 1, I have another point right there, got another point right there, got another point right there. This would be at 10. And so if I draw the points in correctly there and connect them, this should work out just fine. So let me just move that shade down there. There we go. And so what are all these coordinates? Well, the coordinate here looks like it's going to be, I'm not going to give it a letter, but I can definitely figure out what the numbers are of the coordinates. So this would be 6 and going up to 5. So one of the coordinates is 6, 5. This one was all the way out to 10 and to 1, and then this one still at that 1 level. But what's the x value? The x value looks like it's negative 2. So the vertices of the triangle are what we just wrote down there. So let's write them down again. We've got negative 2, 1. We've got 10, 1. And we've got 6, 5. That'd be my final answer for that. Notice, if we didn't draw a careful graph, that would have been extremely difficult to figure out, but drawing a careful graph allows us to find those points exactly where they are. And then so for number 13, it says show that each midsegment is parallel to the sides of the triangle. To do that, you would just show that each midsegment here, these are the midsegments, they're connecting the midpoints of the triangle, that all these slopes, which we've already calculated, all these slopes are the same as the slopes of these sides here. We drew them so that they were, but we could verify it with the numbers as well, and so let's just do that. So the slope of Let's give these some points, or let's give these letters, these coordinates some points. I'll call this x, I'll call this y, and I'll call this z just to make it easier to think about. So the slope of yz, I should say, make it easier to talk about, that's going to be 0 because you're not changing the y values at all. Just the x values are changing, so that's a slope of 0. Slope of, we could look at xy or yx. Either way would be fine to say it. Either way, so this is x1, y1, this is x2, y2. I would say 5 minus 1 over 6 minus -2. And saying that made me rethink what I was doing there. That should not be -2. I don't know what I was doing. Been kind of a rough day here so far. Man, this is not going so well, but hey, I'm catching my mistakes, and I'm going to just make the same mistake over again. No, that should be 2, just plain old 2. Maybe you saw that earlier, and where you were yelling at me, but I couldn't hear you through the internet. It just wasn't working. And so, hey, I caught my mistake. That's what we want to do. If we make mistakes, we want to go back and double check things so that we don't have that mistake staying on our paper the whole way through. So that looks better now. So this is going to be 4 over, this will be 4, which is 1, which is what I expected. So I have parallel slopes. They're the same slope. That means they're parallel. And then the slope of xz is going to be, we would take, I'm going to call this x1, y1, x2, y2. So 1 minus 5 over 10 minus 6 would be -4 over 4, which is -1. And so we've shown that the slopes are parallel because the slopes are the same. So the slopes are the same, I'll say as above, so they must be parallel, so they are parallel. It's kind of like my final explanation there, so I'll box that in. So some pretty intensive problems there in terms of the amount of work we had to show to get the answer. Not hard ones to get, I don't think, but just you got to be careful with your drawing here. You got to be careful with your drawing here to get those ones correct. All right, so find the perimeter now of triangle BCD. That's this big outside shape. This one I think should be a little quicker for us. So this is 9. That would mean that would have to be 9. If this is 12, we know from from the midsegment theorem, which I believe showed up in, is that 5.4? Let's see. Yep, midsegment of the triangle. That should be in this one. So this is half as much. The midsegment is half as long as the segment it's parallel to. So we take that, put that into practice here, or into applicability. We apply that to this problem here, and we get 12 for this one, and this one making the whole thing 24. So this side from here to here is going to be 18, and this side from here all the way to there, from B to D, is going to be 24. So we're going to use these three numbers, 22, 18, and 24, and just add those all together. So 18 plus 22 plus 24. 18 plus 22 is 40. 40 plus 24 is 64. No units given. So that is my final answer. Now let's find the perimeter of STU. So that would be this triangle right here. It's the midsegment triangle, in other words. So again, apply that same theorem. This is 9 and 9. This is half as long as the whole thing. So each midsegment here is going to match up with half the segment of the whole thing. This is 9, that's 9. If this is 24, each one of these is 12. This is also going to be 12. So we're going to add this side right here, 10. That's 12, that's 9. So if we add up 9 plus 10 plus 12, that gives us our answer. 9 plus 10 is 19. 19 plus 12 is 31. So I think I can get rid of this at this point too. Let's figure out these ones now. So 16, write the angle and side measurements in order from least to greatest. I'm going to make some extra lines in this one just to keep things a little neater. Green's fine, I don't mind. didn't lift my pen. I did not lift my pen. And it did the same thing again, but I did not lift my pen. There we go. Okay. Now that my singing time is over, I've got 16 here, angle and side measurements from order from least to greatest. So look here and look at the picture. The smaller the side, the smaller the angle across from it. So this angle C, has the smallest side across from it. So I'm going to go the angles first, and then the sides second. Since that's the way they list them here, I'll go angle first and then side after that. So the smallest angle would be angle C, and then 9 is the next smallest side, so A would be the next smallest angle, and then finally angle B from there. And so the sides from least to greatest, you would say one of the sides, the smallest side, is segment AB, and then segment BC, or CB would work too, and then finally segment AC. So we're doing the same thing with each one of these here. So 17, same idea, angles first, sides after that, and I'll just do that for 18 and 19 while I'm at it. Just write down angles and the sides. Okay, so here's the smallest side here, 23. That means the smallest angle would be angle D. Next smallest side is 25, so next smallest angle is E, and then finally angle F would be the smallest, or the largest angle, excuse me. And so from there, you've got the smallest side, 23 is EF. You've got the next smallest side is 25, so that's FD. You could also say DF. You can switch the order of any of these letters here for the segments, and you still have the same segment. And then finally, ED is the longest one, or DE, either way would be fine. Alright, so from there, let's figure this one out. So this is 50, this is 70. We know that the angles in a triangle have to add up to 180. These two together is 120. That means this would have to be 60 left over here. The same sort of thing works out here and here. You have, so this is just some side work for number 18. I'll put that up here. So this was 180 minus these two added together. In case that wasn't making sense to you verbally, that's 180 minus 120, which is 60. And then 19, you're doing the same sort of thing. This is 90 for the right angle there, plus 55 would be 145, and then 180 minus 145 would be 35. So this angle right here should be 35 degrees. That lets me figure out what the smallest angles are much easier. I need to know that to figure out what's the smallest angle. So angle H, smallest for 18, and then angle J, and then angle G. And then the side lengths, remember the longer side across from a longer angle, smaller side across from the smaller angle. So this is the smallest angle, JG or GJ would be the smallest side. And then 60 is next, so HG or GH would be the next smallest. And then the biggest would be across from angle G, that would be HJ. And so for the angles here in this one, smallest angle is a 35, that's L. And then angle K is 55, and then angle M is the 90. And then the sides are going to be KM across from the 35 is the smallest. LM across from the 55 is in the middle. And KL across from the 90 is there at the end. So it looks like we're good to go. Remember that these segments, the letters in the segments can be switched around and they're still the same segment. Alright, so number 20, you're enclosing a triangular garden region with a fence. You have measured two sides of the garden to be 100 feet and 200 feet. What is the maximum length of fencing you need, and explain? So we could have a smallest and a largest, but we're talking about what's the maximum length of fencing you need. So we want to just think about the largest possibility here. So I'm going to draw a picture. I would highly recommend you do the same on yours. And so I might as well use, since I have the tools so readily available for me, might as well use these tools. I'm going to say this is 100 and this side is 200. So I'm trying to make that, just eyeballing it, make that twice as big. And so remember, this could be coming out this way. It's kind of like on a hinge. Think of it like that. It could be coming all the way out to, if it was totally straight, it would no longer be a triangle anymore, because whatever you have with this vertex and this vertex, or this endpoint and this endpoint, they have to connect to form a triangle. So if I connect them, right now they form a triangle. As long as that isn't perfectly straight, aligned perfectly straight with this other side, they at least make a triangle of some sort. And so this one would be 100. It says 100 feet, so you can use that little dash for feet to represent feet. This is 200 feet. The largest possibility, you would be taking 100 plus 200 to get 300, but it couldn't actually be 300 because then that would just be a straight line, no triangle. So you would say from here it has to be, what's the maximum length of fencing you need? You would say just under 300 feet. I'm saying just under 300 feet for that third side. So this side right here could be, or should be, no more than 300 feet. I actually think the better way to say that would be less than 300 feet, because it can't actually be 300. So let's write it like that instead. So less than 300 feet. And again, if it was exactly 300 feet, you'd have a straight line of fence just doubled over, so that would look pretty ridiculous. You want to have something in your garden here. You need to have something triangular. So what's the total maximum length of fencing you need? You still have to buy the 200 feet of fencing here and the 100 feet of fencing here. So the total fencing would have to be, you could say less than 100 plus 200 plus 300 which would be less than 600 feet. So I think a good way to think about that would be just under. So would you actually have to buy 600 feet of fencing? Yeah, probably. They're not going to sell you 599.999999 feet of fencing. You'll have to buy 600 feet of fencing, but the maximum length you would actually need would be just under, just less than 600 feet. So you would want to buy the actual 600 feet of fencing. Alright, so these ones should be a little bit quicker, I think, too. So AB blank CB, what do we put in there? Is it greater than, less than, or equal to? So let's look at the picture and look at what they give us here. So this looks like it's pretty important to me there and there. This is 88, this is 92. These are the same here and here, and then this is going to be the same matching up in both of them. So we have this idea where it is. This is going back to lesson 5.6 where we have the Hinge theorem, the converse of the Hinge theorem. We've got those two sides and the angle in between those two sides. If the angle in between them is smaller, then the side across from it is smaller. If the angle in between them is bigger, the side across from it is bigger. And the converse of that being, if the side is bigger, then the angle across from it is bigger. If the side is smaller, the angle across from it is smaller. And so what is the case here with this one? This is a smaller angle, so this is going to be a smaller side than this one. So CB, since CB is across from the bigger angle, CB should be the bigger side. So the alligator should be eating the CB because that's bigger if you learned it that way. So this one, what goes in the blank? That goes in the blank. Just the less than sign. AB would be less than CB because it's a smaller angle across from that side. 22. Measure of angle 1 is blank compared to the measure of angle 2. Now these things look parallel, but we can't necessarily say that they are parallel. I can see that this is true, and so I noticed that this one was smaller than this one, and this one is across from angle 1, this one's across from angle 2. And we have those two corresponding congruent sides like we need to have, and so the angle in between them the one that matches up with the smaller side is going to be the smaller angle. So this one, measure of angle 1, should be less than measure of angle 2. So this one happens to be less than, again, 23. TU is what compared to VS? So if they're both the same, which is the case here and here, this angle is the same as this angle, they're both 126, that means the sides across from them should also match up. They should be equal to each other. So this would be filled in with an equal sign. So 23 should look like that. And then 24. Write just notice it says the first statement. You don't have to write the whole proof out in this case, but the first statement for an indirect proof in this situation. In a triangle MPQ, if angle M is congruent to angle Q, then MPQ is isosceles. So I think drawing a picture first is helpful to understand the situation and what we would need to do for an indirect proof. You could say MPQ, M is congruent to Q, so these two angles you're saying are the same in the actual triangle. And so why would this be isosceles? So we could say, or we would assume, that the opposite of what you want to prove is true first of all. So by definition of isosceles, or what isosceles means is that this one would actually be congruent to this one. So we would want to prove the opposite of that, or we would want to assume that the opposite of that is true to start. So we assume the opposite of what we're trying to prove is true. So we would say assume that MP is not equal to QP. I think a good thing to say before that might be given that, so we are given that this is actually true. We can't change the fact that that's true. So given that angle M is congruent to angle Q in a triangle, and then we'll assume, so I'll make that a lowercase a, we would assume that MP is not equal to QP. Assuming that's the case, going through the proof, eventually we would get a contradiction where this can't be true at the same time that this part is true, and so we would therefore have the proof indirectly that these two things would have to be congruent to each other, but we're not going through the whole proof here. We're just saying that first step and stopping at that point. So 25, final problem here in this chapter review. Now we're writing the whole proof. So proof that no triangle has two right angles. So we would have something like this for a triangle to actually have two right angles. Let's go with PQR. So we're going to assume a false picture. We're going to assume that this is true, that this is a right angle and this is also a right angle. So starting our proof here, we're going to assume, we're trying to prove that no triangle has two right angles, so we're going to assume that it does. We're going to assume the opposite of what we're trying to prove is actually true. Assume that a triangle has two right angles. And so I'm going to say as shown in the picture. As shown in the picture. So I'm kind of using, the book uses triangle A, B, C, and does that. So I'm giving you just a different way to prove the same thing, still using the same idea though. So assume that a triangle has two right angles shown in the picture. I would hope you look at that and say clearly that measure of angle P then equals 90 degrees and the measure of angle Q equals 90 degrees. You could also say by the triangle sum theorem, we know that the angles in any triangle are supposed to add up to 180. So that's just something we know about triangles. By the triangle sum theorem, the measure of angle P plus the measure of angle Q plus the measure of angle R has to equal 180. That's just something that's always true about triangles in Euclidean geometry. But then we could say, but since the measure of angle P plus the measure of angle Q equals 90 plus 90, which equals 180, we would have to say that that means that the measure of angle R would equal 0. That has to be true. If this 90 plus 90 here, the only way to get this plus this is 90 plus 90 plus something else equals 180 would have to be where this is 0. So the measure of angle R equals 0. And let's word it like this and say something like it's not possible rather than saying this, but it's not possible for an angle in a triangle to have a 0 degree measure, to have a measure of 0 degrees, in other words. And so we can say therefore we have a contradiction and we can doesn't look like very good. We can say that no triangle has two right angles. So we assumed the opposite of what we wanted to prove was true. We got to a contradiction. That means what we assumed at the beginning could not be true, therefore the opposite of that has to be true. The opposite of that being that no triangle has two right angles. So that finishes up our chapter review there for chapter 5. Go back to any of those problems if you need to. Pause, rewind, review any of those problems as needed, and be ready for the test coming up on chapter 5. Hope you found that helpful, and please let me know if you had any questions in class.